Hello, and thank you for logging into my talk. My name is Eran Amichai. I am a postdoc at Dartmouth College in Hannah Hofstede's lab. And I want to talk about a project we're doing in collaboration with David Boerma, Rachel Page, and Sharon Swartz, studying the sensory role of whiskers in Nectivorous bats. This project started about 10 years ago when I asked to join Dr. Armando Rodriguez Duran's lab as they study a cave in Puerto Rico where bats emerge and boa snakes try to capture them. He invited me to tag along. We went there, we captured bats and witnessed this really breathtaking natural event as hundreds of thousands of bats emerge almost over 2 hours, 5 different species. We managed to capture a few, and that gave me the first chance I ever had to really look up close at a Nectivorous bat species, this Monopholos redmani, this guy over here. And for me, the first thing that attracted my attention was their whiskers. They have these long vibrissae that you can see here that are all pointing forward, almost like a brush around their muzzle, and all end in a perpendicular plane to the muzzle itself. And that was very, very different when I compared to all these other species that I'm familiar with from the Mediterranean that have unremarkable typical whiskers that you would expect to see on mammals. Now, that got me thinking that these whiskers have to do something with the diet of this bat. And we do know that mammalian whiskers are sensory organs. Yeah, they have a big variety of functions. Rodents, for example, use them to estimate the width of passages they run through or to detect obstacles. Pinnipeds use their whiskers to detect underwater water flows. They can even track or follow wakes that fish leave behind them as they swim. We know that cats use their whiskers to guide their bite into precise locations. And we also know that there are sensory hairs in bats, although these are not the whiskers. But for example, we have bats that use hairs on their wings to detect air vortexes and optimize their flight biomechanics. And this species here, the greater mouse-tailed bats from the Middle East, have these sensory hairs on the tip of their tails, and they use that almost like a reverse camera. As they walk backwards, they back into these crevices in the rocks, as you can see in the picture, and they move their tails from side to side, almost like a blind person would use a cane in order to feel their way and make sure that it's clear. However, nobody has ever studied whiskers in bats, and we figured this is a good opportunity to start doing that. Now, many neotropical fruit bats from family Philostomidae have either partial or main component of the diet that is nectar. And we know that Nectivorous bats are essential pollinators for many flowers, for example, Passiflora, bromeliads, columnar cacti species that rely on bats either as primary or secondary pollinators. And many of these flowers have this typical tubular, deep body that is a typical shape for a bat-pollinated flower or a bird-pollinated flower as well. And these bats, just like hummingbirds, hover in front of the flower when they're about to eat, and then they keep hovering as they stick their head into the flower, stick their tongue out, and drink the nectar. And at the same time, they're also collecting pollen on their fur, which is the payment they provide to the flower when they take this pollen to other flowers. Now, this event, this hovering, is expensive. It's expensive energetically. Hovering flight is very, very energetically demanding. It's also exposing the bats to risk, because when they're hovering in front of the flower, right next to it, or with their heads inside, they are in risk of predation. And many pit vipers, eyelash vipers, for example, love to ambush next to these flowers and catch bats or hummingbirds as well as they are feeding off of the flowers. Now, when I said that this is an unusual arrangement of whiskers, this was, of course, comparing to bats that do not feed on nectar, but when you compare it to bats that do feed on nectar, you find that this structure is actually not that unusual, and many other species display it as well. So the hypothesis we have here is that the whiskers provide the bat with information about its positioning within the flower, and it uses that information to optimize its hovering flight and its feeding event, to reduce those risks and costs. And to study this, we formed the bat whisker team with Sharon Swartz, who heads the aeromechanic evolutionary morphology lab at Brown University. She uses high-speed cameras to study kinematics of bat flight. We also collaborated with Rachel Page, who heads the Sensory and Cognitive Ecology Lab at the Smithsonian Tropical Research Institute in Panama. And she is an expert on neotropical bats and have also access to several species of nectivorous bats. For example, Glossophoca sauricina, which you see here, which is the species we ended up using. And we figured that what we're going to do is we're going to manipulate the whisker length. We wanted both to prolong them and to clip them. Ended up only clipping them due to what we could and couldn't do. And we figured that if we manipulate, if we clip the length of the whiskers, what we're going to see is we're going to see an effect on the depth within the flower, both of the bat itself and how deep they are when they extend their tongue, how smooth their approach is. The total hovering time would probably, we predicted, would become longer when the whiskers are clipped, and the head and body alignment relative to the center line of the flower, we predicted would be different as well. To study that, we built up this system. So we have these glass flowers that we used instead of flowers, instead of reed flowers. We had two high-speed cameras that were positioned in a way that gave them an overlapping field of view, so we could extract three-dimensional information later from the videos. I brought my bat beautician kit. Very important to have at least 2 colors of eyeliner. You need a good pair of tweezers, good scissors, high-quality eyelash extensions, and then we had the bat themselves. And this is a Glossophoca sauricina bat with the whiskers still intact here. And you can see this typical brush-like structure. And here is how it looks after we've clipped the ventral and the lateral whiskers for our treatments. And the resultant videos are these high-speed, slow-motion videos, 450 frames per second. We have a front camera on the left, side camera on the right. You can see the bat approaching now, probably using echolocation. And you can see those marks we have on the face of the bat. So these are landmarks we use later for extracting the motion. Now the bat is going to enter the flower, just like it enters a real flower, and then extend its tongue and drink from the nectar. And our first piece of conclusion from these videos is that, wow, this is amazing. This really is a fascinating thing to watch, especially in slow motion. I could watch hours of these videos. I have, in fact, watched hours of these videos, and they are just as mesmerizing when you watch them 150 times as when you watch them the first time. So it was really a pleasure to do this, this study. And then we take these videos and we put them in this open source motion tracking software called XMALab. We use these landmarks that I showed you before to extract the 3D coordinates and then recreate the trajectory of each of these landmarks to analyze the spatial movement of the bat within the flower. These are the landmarks that we used. The 2 most important ones are this, the upper lip, this point, and the eye, that is the other point. And we measured bottom clearance or side clearance of those points. We measured depth of tongue extension. We measured time of the event. We also measured the angle of the head tilt as the bat was moving inside the flower, and we predict that this angle would be more acute as the bat is with clipped whiskers rather than intact ones. We had 11 individuals, all male, Glossophaga suricina. We had an average of 8 flights per individual for control and 7 flights per individual with treatment with clipped whiskers, and a total of 158 flight events that we could analyze. And the preliminary results are very promising. We are very encouraged by them, and we really hope that the full set of results will show the same picture. What we have here is control flights of one individual in blue, and in green you see the same individual when it flies with clipped whiskers. The x-axis is the frames, so basically it is time, 0 being the entry to the flower, and our point of reference or our data here is from the movement of the upper lip landmark. So the point that we painted on the upper lip of the bat. The x-axis, sorry, the y-axis is the height of the bat relative to the center or to the bottom of the flower. So 0 on the y-axis would be the bottom of the flower, the floor of the flower, you would say, and 0 on the x-axis is when the bat enters. And you can see that there's no real difference between control or treatment when the bat is approaching the flower. However, as soon as it is in the flower and presumably starts using sensory information from the whiskers rather than echolocation, we see that the two separate. The green, the trial, the clipped whiskers are much closer to the bottom of the flower rather than to the center of the flower when we talk about the control. We see a similar picture when we look at the movement of that same landmark, the upper lip, on the z-axis, so left or right of the center of the flower. Again, no real difference between control and treatment as the bat approaches, but as soon as it enters the flower, the two separate, and we have a much less centrally aligned movement within the flower when the whiskers are clipped. We also see, again, as we predicted, that the total duration of the event in green is longer compared to when whiskers are clipped compared to control when the whiskers are intact. So this is very, very encouraging. We hope that the rest of the results show the same picture. But we wanted to study this from also a different angle, from a morphological and phylogenetic angle. And to do that, we used specimens from the American Museum of Natural History. We took individual bats from 10 different species divided into 4 different groups. 3 groups are within family Philostomidae, and these are the green, blue, and red species. So 9 different species that we tried to take with more or less the same distance from each other phylogenetically within the group as outside of the group. And this group, the green guys here, these 3 species, they have a complementary component of Nectivorous in their diet. So they are mostly frugivorous, but they would eat nectar when they can. It is not their main staple of diet. In blue, you see the species that are obligatory Nectivorous. So the main component of the diet is nectar, and in red are species from the same family, but they have no Nectivorous at all in the diet. They can be either frugivorous or insectivorous as these 2 species. The last group is one species that is an outgroup, so not from the same family, but a different family. And what we measured is the length of the whisker. In this case, this is the ventral whisker of an individual and compared that to the height of the skull at the point where the whiskers grow. And we extracted this ratio between the length of the whisker and the length of the height of the skull. We did the same for the lateral whiskers, comparing their length to the width of the skull of where they grow. And these ratios basically tell you how long the whisker is compared to the size of the head of the bat. And you can see that these ratios are much, much higher for the Nectivorous species. Again, this is not the final data set, but we're getting there. We haven't done the entire analysis yet, but it seems to support our hypothesis that the whiskers are long because of the diet and not because of phylogeny. So we are, again, very encouraged to have our hypothesis seemingly supported by two avenues of investigation, the morphological phylogenetical one on one side and the behavioral on the other. So with this, I want to help, thank you for listening to this talk. I would like to thank once again the entire whisker team or whisker crew, bat whisker crew. It's Hannah Hofstede from Dartmouth, Rachel Page and Greg Cohen from STRI. Greg, without him, the project would never have taken off. Sharon and David from Brown, and Armando Rodriguez Duran, whose hospitality provided the spark that started this project. Benjamin, Alberto, Sydney, and Ray that helped with working with the software and extracting the information. The project was supported by the Traveling Fellowship of the Company of Biologists. I would like to thank them as well. And great collaboration and cooperation from the American Museum of Natural History that provided the specimen for the morphological study. I would also like to thank my volunteer bats, the Glossophaga suicina, who sacrificed their whiskers to satisfy my curiosity, without whom nothing would ever work. And if you have any questions, I would be happy to answer either at the SICB Plus chat or on my email or Twitter handle, which you can see at the bottom right of your screen. So with that, thank you again. I hope you enjoy the rest of the talks in the conference, and have a good day.